So we have gone to a little more, we have started with hydrostatic problems. Now we have moved to perfect fluids in the steady state. Look, in that regime. We have looked for solution in that regime. Let's see what can do under this hypothesis in this transient state. Let's see what we can do. So now we are moving to barotropic, water is barotropic, perfect, water is perfect, potential forces, but now for the transient solution. So we are in this situation, okay? We are in this situation. But now let's consider two possible simplifications for specific flows, for specific problems, which are the flow is irrotational and the flow is potential and incompressible. Potential or rotational, which is the same, and potential and incompressible. By the way, what is a definition of a potential flow? Potential flow or irrotational flow. You know, this is the expression of the rotational, of the rotation of the velocity, right? And we already saw in the first part of the course, when we talk about rate of strains, we define the vorticity. The vorticity, and I think we have it here, right? Somewhere. We have just seen that in somewhere here. Where is it? Here. Okay, this is the rotation, the vorticity. So the vorticity which can be expressed, the vorticity is precisely that expression, the rotation of the velocity, is the vorticity. What is the vorticity measuring? The turn, the velocity of rotation, the rotational velocity of the fluid. So a fluid which is very laminar, with no vortices, normally can be considered irrotational. What is our case? Well, many fluids, for instance, fluid canals. Vortices are not very common there, so we can consider that the fluid canals or the fluid in pipes. Many cases, we can consider the fluid in rivers, for instance. We can just make the assumption, sometimes it's a stronger or weaker assumption, that the rotational of the velocity is zero. So let's do that hypothesis. So now we are in the situation of irrotational. Look, if the rotation is zero, that means the vorticity is zero, and then we proved that also in chapter 3. We said that if a vector has a rotational zero, that vector field is potential. So there exists a scalar whose gradient returns the velocity. We proved that. Okay? So just by assuming that the flow is irrotational, that there are no vortices, then we can assume that the velocity field is quite simpler than the general case. It's just the gradient of a scalar. So the real unknown is that scalar, because if I know the scalar function, just by taking the gradient, I can know the velocity. Okay? So this is the case. That is what the concept of irrotational flow is associated at the case of potential flow. Potential flow would be that case in which the vector field of velocities comes out from differentiation of potential. And irrotational means when the vorticity, the rotation of the velocity, is zero. Both terms are equivalent. Okay? If it's rotational, it's potential. If it's potential, it's rotational. Okay? So now that hypothesis means that we can assume that the velocity is the gradient of a certain potential. Let's call this potential kappa, in principle, as a function of the space and time. Okay, so now let's go back to the problem, and now let's replace B, every time we see B, as the gradient of this kappa. So that equation here. So we have the Bernoulli's trinomial here. Here, this is no longer zero because the velocity field is no longer steady state, stationary. But then the velocity of B with respect to t can be understood as the derivative of this gradient of kappa with respect to t. So now, and what happens with that vorticity? Vorticity is 0. So for this specific case, the motion equation, the Euler's equation, the momentum balance equation, can be expressed in that way. Gradient of m is equal, look at that. Why don't we, this is a gradient, why don't I pass that to the other side? So I pass that to the other side and see that the gradient of a function, which is not a trinomial but a quadrinomial, which is the generalized pressure plus the potential forces, the potential for forces, plus the velocity squared, plus derivative of kappa with respect to t is equal to 0. So the gradient of something is equal to 0. Everywhere. There is no restriction where here. Everywhere. So what can we say about this something? If the gradient of something is 0 for any space and any time, what can we say about this something? What can we say? Constant with respect to x. Because all derivatives with respect to x is equal to 0. Okay? So that's what it is. So functionally, that means that these 4 terms here is just a function of t. So we have integrated it. You know? Well, accepting a constant, this plays the role of a constant in this integration, because we have integrated with respect to space, with respect to x, and it remains a constant with respect to t. Okay? These constants can be eliminated, finally, by defining this associated in kappa bar. So finally, that equation looks like that. It's an equation in which, you know, it's still a partial differential equation. Look. A partial differential equation, but look at the knowns of differential. This is a very famous equation, Holly, also. This is what is called the equation of hydraulic transients. Because this equation is a much simpler equation that can be solved by simple numerical methods, typically finite difference methods, to solve what? Typically that kappa. Okay, so the questions are those. Look, for these cases, potential, or which is equivalent to rotational flow, the real equation is not the velocity, is the kappa, because the gradient of kappa is the velocity. Okay? So look, the questions are that. By replacing the velocity by gradient of kappa, we have that equation, which is the continuity equation, now in terms of kappa. That equation, which is the one that we have integrated the hydraulic transients equation, which is a function of kappa. And then, since the fluid is still barotropic, that equation. Okay, how many equations have here? One equation, that's one. This is one equation, this is a scalar, so this is one equation, and this is one equation. But how many unknowns do we have? This rho 1, p1, kappa 1, 3 equations. So this is a much simpler problem. The original problem had 5 equations and 5 unknowns. And now, by this treatment, whenever we do the assumption of a rotational flow, we have a much simpler problem, which is a potential flow, very important. There are many finite element codes that solve the potential flow problem. And they are really efficient because they solve a simple problem, 3 equations with 3 unknowns. Okay? Look, what happens is on top of that, so incompressible, so in rotational flow, we are talking about perfect fluid, potential forces, transient solution, look, it's transient, not steady state, and in rotational flow. But now, let's assume that being barotropic is even extended to the case of incompressible, which is a specific case of barotropic. If that is the case, density is constant, P, we saw that is the pressure divided over 0, the equation of motion is that, and then the density is no longer an equation, so we have 2 equations with 2 unknowns. 2 equations is the equation in the density, that part of the density disappears. This, by the way, the divergence of the gradient is the Laplacian operator. So that is a typical equation. Mathematicians use that. Probably in computation, in numerical methods, you use that equation many times. Laplacian of something equal to 0. That's the Laplacian equation. Laplacian of something is equal to 0, and then On top of that, we have this other equation, which is the linear momentum balance. Two equations with two unknowns. What unknowns? Pressure and the potential function, which is, because density is no longer an unknown. Since the problem is uncompressible, density is the initial density, which is supposed to be known. Even easier. Okay?